Module 8, Chapter 5.2, Exponential Functions. Use your calculator to evaluate the following. Round your answer to the nearest thousandth. Y equals, 3 to the power of square root of 5. 3 to the power of the square root of 5, which would give us 11.66 to the nearest thousandth would be 11.665. 1/3 to the square root of 2. So in parentheses, 1/3 to the power of the second square root of 2, close the parentheses, and we get 0.21146, or to the nearest thousandth would be 0.211, and the square root of 8 to the square root of 8. The second square root of 8, close that parenthesis, to the power of the second square root of 8 will give us 18.9305 or 18.931. Power functions versus exponential functions. Recall, a power function is a function of the form f of x equals x to the b, where b is a constant. If the constant is 1 over n for some integer greater than or equal to 2, then we call that function a root function. If f of x is equal to a to the x, where a is greater than 0 and is not equal to 1, then f of x is the exponential function with the base a. Now remember, a power function, the variable is the base. An exponential function, the variable is the exponent. Now, if a is greater than 0 and a is not equal to 1, then f of x is equal to a to the x is the exponential function with base a. Now we are extending the exponents to include all real numbers, not just the rational numbers. Now, if you'll remember a few properties for exponents, a to the x is a unique real number. A to the b is equal to a to the c if and only if b is equal to c. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. And if a is between 0 and 1 and m is less than n, then a to the m is greater than a to the n. Now, if we're looking at the graph of the exponential function a to the x, for a is greater than 1, that means the base is greater than 1. Then the domain is from negative infinity to infinity, and the range is from 0 to infinity. Your graph of your exponential function starts over in the second quadrant and rises up to the first quadrant. And if you put it in your calculator, you get a graph like this middle picture. And if you look at a table, this is the graph for 2 to the x power, then you get some table values. Now this function, f of x equals a to the x for a is greater than 1, is increasing and continuous on its entire domain. The x-axis is the horizontal asymptote as x approaches negative infinity, and the graph will always go through the points -1, a to the -1, 0, 1, and 1a. Okay, let's do an example for the graph if a is greater than 1. Graph the function f of x equals 2 to the x. Determine the domain and the range. So if we were just plugging points, we always start with 0 and 1. If x is 0, 2 to the 0, well, anything to the 0 is 1. If we plug in x to the 1, x is 1, we get 2 to the 1, which is 2. Now, if we wanted to just do a few more, we could plug in 2. That would give us 2 to the second, which is 4. If we plugged in negative 1, that gives us 2 to the negative 1, which is 1 over 2 to the 1, which is 1/2. And we're going to, if you'll notice, we're going to get the shape if x is 0, y is 1. If x is 1, y is 2. If x is 2, y is 4. If x is negative 1, y is 1/2. So we are going to get this little picture right through here. This side is going to take off and go to infinity, and this side is going to take off and get closer and closer and closer to the line y equals 0, but never cross it. Now, if your function f of x equals a to the x, and a is between 0 and 1, meaning a is a fraction less than 1, then we get the same shape function, but it starts up high in quadrant 2 and comes down low in quadrant 1. Now, in this case, f of x is decreasing and continuous on its entire domain. The x-axis is the horizontal asymptote, and the graph goes through the point -1, a to the -1, 0, 1, and 1a. Do an example. To graph f of x equals 1/2 to the x, determine the domain and range of f. Well, let's plug our points again. If x is 0, we get 1/2 to the 0. Well, anything to the 0 is 1. If x is 1, we get 1/2 to the 1, which is 1/2. If x is 2, we get 1/2 to the second power, which is 1/2 times 1/2, which is 1/4. If x is -1, we get 1/2 to the -1, which means reciprocal, which means 2. And when we plot that, we get over 0 up 1, over 1 up 1/2, over 2 up 1/4, then back on the other side, back 1 up 2. So we're getting the same shape of a graph. It's just flipped because the base is a fraction. Now, explain why the graph of g of x equals 1/2 to the x power is a reflection across the y-axis of the graph f of x equals 2 to the x. Well, as a hint, remember to show a reflection across the y-axis, we must show that f of x is equal to g of -x. So f of x is equal to 2 to the x. If we plug in -x, g of -x, then we would get 1/2 to the -x, but a negative exponent means reciprocal, so that would be 2 over 1 to the x, which is 2 to the x. Explain how the graph of y equals -2 to the x plus 3 is obtained from the graph of y equals 2 to the x power. Well, 2 to the x power, remember we said it goes to if x is 0, y is 1, if x is 1, y is 2. So that one would come around like this right here. That's 2 to the x. Plus 3 means we shifted up 3 places, 1, 2, 3. So now it's going to be up to here. And then the negative out front means we're going to flip it. So if this was our horizontal asymptote right here and we flip it across that, then we end up with that graph, this pretty blue line, which is -2 to the x plus 3. But in terms of graphing, you guys can just plug it into your calculator. let's use a graphing calculator to evaluate some of these exponential expressions. So if we wanted to do this on our calculator, we would do 0.5 to the power of negative second square root of 2. And that would give us 2.665. Now, let's solve some exponential equations. 25 to the x power is equal to 125. Well, do you remember one of the properties earlier that said if a to the m is equal to a to the n, then m has to equal n? So if we go through and say 25 to the x power, well, 25 to the x is the same as saying 5 squared to the x, or 5 to the 2x. Now 125 is 5 times 5 times 5, which is 5 to the third. So if 5 to the 2x is equal to 5 to the third, then 2x has to be equal to 3, or x has to be equal to 3 over 2, or 1.5. Okay, let's do another one. 1/2 to the x power equals 8. Well, 1/2 can be written as 2 to the negative 1 to the x, which is 2 to the negative x. 8 can be written as 2 to the third. So if 2 to the negative x is equal to 2 to the third, then that means negative x has got to equal 3, or x has got to equal negative 3. 5 to the 2x plus 1 equals 25. How would we solve that exponential equation? Well, 5 to the 2x plus 1, 25 can be written as 5 squared. So if we have the same bases on both sides, that means then the exponents must also be the same. So if we went through and said minus 1, we'd get 2x is 1. Dividing by 2 would give us x has to be equal to 1/2. Okay, little typo here, but let's solve the equation 1.5 to the x plus 1 minus 27 over 8 to the x power is equal to 0. Well, remember 1.5 is the same as 3 over 2 to the x plus 1. 27 over 8, well, that's the same as saying 3 over 2 to the third to the x is equal to 0. So what we get is 3 over 2 to the x plus 1 minus 3 over 2 to the 3x is equal to 0. Now, these are just working out that they've got the same basis. Sometimes you may not, and in that case, we would just go through and use our calculator. Now, on this one, we've got 3 over 2 to the x plus 1, and really, I guess we're supposed to have parentheses around that. Now, on this one, if we add 3 over 2 to both sides, we get 3x. So what we end up with is, if the bases are the same, then the powers have to be the same, so x plus 1 has got to be equal to 3x. Now, subtracting an x from both sides, we get 1 over 2x, which means that x is 1/2. Now, if we wanted to do these on our calculator, we're going to come up here and we are going to do y equals 1.5 to the power of x plus 1 in parentheses minus 27 over 8 in parentheses to the power of x. And then we're going to let y2 be 0. Well, when we graph it, we get a picture that looks like that. To find where they intersect, we're going to go second trace, or second calculate, number 5. Enter, enter, enter. And we get a solution of x is 0.5, which is what we got as 1/2. Now, use your graphing calculator to solve the inequality 32 to the x is less than 16 to the 1 minus x. Now, on our calculator, we're going to go up here and we're going to say y equals 32 to the power of x. And then the second one we're going to do is 16 to the power of 1 minus x. It's hard to see that in there. Let's zoom in just a little bit. Zoom to, intersect, we could go to window, change our y values maybe up to 10. That's going to take our graph just a little bit higher. So there's your 32 to the x. There's your 16 to the 1 minus x. Find where they intersect. Second, calculate number 5. Enter, enter, enter. And we would get x is equal to 0.444. Now, the natural number e is named after the Swiss mathematician Leonhard Euler. E involves the expression 1 plus 1 over x to the x. And what it means is, as x gets larger and larger and larger, the expression 1 plus 1 over x to the x gets closer and closer to 2.718281828 and so forth. So that's why we have e as a constant of 2.718. E is an irrational number. It never ends, it never repeats, and unlike most variables, e is fixed. It will never change. Now, since e is an important base, calculators are programmed to find powers of e. Now, in terms of applications, recall your simple interest formula. I equals PRT, which means principal times the rate times the time, where P is the principal or the initial investment, R is the annual interest rate written as a decimal, and T is the number of years. If A is the final balance at the end of the year, then the first year we would say it's the principal plus the principal times the rate, which would give us P times 1 plus R. The second year, it would give us the amount at the end of the first year plus the amount at the end of the second year. So our formula becomes A equals P times 1 plus R to the power of N. Our compound interest formula that you will need to know for the test. Suppose that a principal of P dollars is invested at an annual interest rate R in percent, compounded N times per year. Then the amount A accumulated after T years is given by the formula A equals P times 1 plus R over N to the NT power. So let's do one. Suppose that $1,000 is invested at an annual rate of 8%, compounded quarterly. Find the total amount in the account after 10 years if no withdrawals are made. So our formula says I equals P times 1 plus R over N to the NT power. P is the principal, which is 1,000, times 1 plus the rate is 8%, divided by, now the N is the number of times it's compounded per year. So compounded quarterly means 4 times per year, and we are doing that to the NT power. So N is still our 4 times T is 10 years. So we would get 1,000 times 1 plus, now if we pulled out the old calculator, if we did it in pieces, 0.08 divided by 4, so that is 0.02 to the 40, are 1,000 times 1.02 to the 40, which is 1,000 times 1.02 to the power of 40, which means our total interest would be $2,208.04. If P dollars is deposited at a rate of interest R, compounded continuously for T years, the final amount A in dollars on the deposit is A equals PE to the RT power. This is what we call the PERT formula. It's the principal times E to the power of the rate times the time. So, for example, A equals PE to the RT. Suppose $5,000 is deposited in an account paying 8% compounded continuously for 5 years. Find the total amount on deposit at the end of 5 years. So P is our amount of principal, which is $5,000, times E to the RT. Now R is 0.08 times 5. So if we pull out the calculator, we would get 5,000 times E, which is down here on the bottom right above that LN button, to the power of, now notice they've already got a open parenthesis for you, so I'm going to put the 0.08 times 5 inside the parentheses, which gives us a dollar amount of $7,459.12. Another application of exponential functions, the chances of dying of influenza or pneumonia increase exponentially after age 55 according to the function defined by f of x equals r times 1.082 to the x power, where r is the risk in decimal form at age 55 and x is the number of years greater than 55. And compare the risk at age 75 with the risk at age 55. Well, the first one, f of 75, means r times 1.082 to the x, where x is the number of years greater than 55. So 75 would be r is 20. F of 55 means r times 1.082 to the 0, because it's the number of years greater than 55, which if we used our calculator on that, then we would know that 1.082 to the power of 20 gives us 4.84 times r, which means the risk is 4.84 times greater at age 75 than at age 55. Another application of exponential functions. Since 1990, world population in millions closely fits the exponential function defined by y equals 5,282 times e to the 0.01405x, where x is the number of years since 1990. The world population was about 6,080 million in 2000. How closely does the function approximate this value? Well, the formula says where x is the number of years since 1990, and we're talking in the year 2000, so for our problem, x is going to be 10. So it'd be 5,282 times e to the 0.01405 times 10. So if we did that on our calculator, we would get 5,282 times e to the power of 0.01405 times 10, because it is 10 years after 1990, and that would give us 6,078.78. Now that was based on the formula, whereas actually it was about 6,080 million. So I mean, we're pretty close. We're within 1.5 million. Now it says use this model to approximate the population in 2005. Well, in 2005, that's 15 years after 1990. So we're just going to come on to our calculator. Remember, second enter is a repeat command. And I'm just going to go in here and change our to the power of 10 to the power of 15. And when we do that, we are predicting that population in the year 2005 would be 6,521.18 million for the population. And then also it says use the model to predict the population in 2010. Same thing, we're just going to go into our calculator. Everywhere we had an X, we're going to plug in 20. So using that same little second enter, that pulls up the previous screen, and then we can just change the 15 to 20, which would give us a value of 6,995.76, so almost 7,000 million. Okay, you are now ready to complete this section of homework on MyMathLab.